Hello and welcome to this TI Precision Lab discussing frequency planning for high-speed ADC systems. In this video, we'll discuss the concept and benefit of frequency planning. We will also look at some simple tools that can be used to help with the planning process. First of all, what is frequency planning? First, we need to compare an ideal ADC signal capture scenario with that of the real world. This image shows the ideal signal spectrum of F1 captured by an ADC. This next plot shows the desired signal along with several harmonics of the signal. Any real data converter will have some harmonic distortion. If harmonics or other distortion products overlap the desired signal, system performance may be degraded. So how can we optimize the performance of the received system despite the limitations of real-world converters? The relative location of the signal and harmonics is a function of the input frequency and the sample rate of the ADC. Changing to a higher sample rate will move the relative position of spurs in the spectrum, thereby improving system performance. Harmonics are the most common spurs that will be encountered. Interleaved ADCs may exhibit spurs resulting from the minor mismatch in offset, gain, and timing between the sub-ADCs. This table lists the expected spurs for interleave by 2 and interleave by 4 ADCs. TI provides a spreadsheet-based tool that makes it easy to visualize the locations of the signal of interest and the common harmonics and interleaving spurs. So what variables do we have at our disposal to accomplish frequency planning? The frequency planning spreadsheet available from TI has the following user input fields in the upper left: ADC sampling rate in megasamples per second, ADC interleaving factor, factors of 1, 2, or 4 are currently supported, and the signal center frequency in megahertz and signal bandwidth in megahertz. Once these parameters are entered, a visual representation of the first Nyquist zone is shown. The x-axis shows frequency, while the y-axis shows the fundamental, interleaving tones, and second to fifth harmonics. The most prominent overlap tone is identified in the overlap field. Once the initial overlaps are understood, the user can update the ADC sample rate or input signal parameters to determine the best combination to eliminate or minimize overlap. In this example, we have an ADC sampling at 4,000 megasamples per second. This ADC uses 4 interleaved sub-ADCs. The input signal is centered at 5,000 MHz with a 300 MHz bandwidth. At this sample rate, there is overlap between the fundamental and HD3, HD5, and one of the interleaving tones. If the expected level of these spurs will be large enough to impact system performance, the sample rate can be changed to prevent overlap. If the sample rate is changed to 5,500 megasamples per second, the input signal does not overlap with any of the harmonics or interleaving tones. This illustrates the powerful capabilities of studying the frequency plan and adjusting the sample rate to improve system performance. That concludes this TI Precision Labs video. Thank you for watching.